Hi, this video is on hypergeometric distributions. It's an introduction to the hypergeometric distribution and the formula. So we're learning to identify and solve problems using hypergeometric distributions, and hopefully at the end of this video you'll be able to explain the difference between the hypergeometric and binomial, know when to choose a hypergeometric, know where the formula comes from, know what the various parts of that formula represent. M is on the calculator rather than D, and know how to use the NCR function to solve the problems, and know how to use the CAS to solve them as well. So we're going to start with a typical problem. Now we have 10 coloured balls in a bag. 4 are blue, 6 are not. You take 5 balls out. What's the probability that exactly 3 of them are blue? So far sounds a little bit like a binomial distribution problem, but there is a key difference here, and that is that as we take the different balls out, the probabilities change. So because the probabilities aren't fixed, which we need for a binomial, we need a different way of solving it. So let's start with saying, okay, we take one ball out and it is either blue or it's not blue. Now the chance of it being blue is 4 in 10, because we have 4 blue and 10 in total. Not blue would be 6 in 10. Then the next one could be blue or not blue. That would be now 3 out of 9, because there's only 9 to choose from. We've already had one blue one, so there's only 3 successful ones left. And then 6 and 9 for 6 out of 9 for the not blue. I'm not going to fill in the entire tree diagram. It would carry on underneath here. We'll just go on to the third one. We could have blue and not blue again. This time it would be a 2 out of 8 chance of getting a blue, because there's only 2 left. There's only 8 balls left. 6 out of 8 for not blue. Again, we could have blue and not blue up here, where we'd have a 1 in 7 chance of getting a blue, because there's only 1 left and only 7 balls left to choose from. And finally down here we'd have a 1 in 6 chance of getting a blue and a 5 in 6 chance of getting not blue. And I won't quite fill in that whole table. Now, if we have a look at this, one successful path through this would be to get blue, 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 not blue, and not blue. So that's giving me exactly three blue balls. Blue, 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 not blue, not blue, which is 4 on 10 times 3 on 9 times 2 on 8 times 6 on 7 times 5 on 6. But there are lots of different ways that we could get 3 blue balls and 2 not blue balls. So another possibility might be if you went not blue, 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 blue. And those probabilities would be 6 on 10, because there's 6 not blues and 10 to start off with. Then the next one there would be 5 and 9. Then we'd get a blue. Our first blue would be 4, second blue would be 3, third blue would be 2, over 8, 7, 6. So you can see the numbers at the bottom here, the denominators are the same, but these numbers at the top have changed, but only in order. So we actually get the same value when we work out this different order. So the question really then is, how many different ways are there to get 3 blues and 2 not blues? So how many possibilities are there? Now, the way to work that out is that there would be 5 in total, so 5 factorial, and 3 would be the same and 2 would be the same, which is 5 factorial over 3 factorial, 2 factorial. So 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. So that 3 times 2 times 1 is going to cancel out there. That 2 will cancel out there, leaving us with 10. So there are 10 possibilities in total. So it would be 10 lots of it doesn't matter which one we use, the 6 times 5 times 4 times 3 times 2 times 1 over 10 times 9 times 8 times 7 times 6. Okay. And if we work that out in the calculator, we get 5 out of 21, or 0.2381 for decimal place. So just to put that back into the context of the question, the probability that we get exactly 3 blues when we take 5 out of a bag of 10, where 4 are blue and 6 are not, is 23.81%, or 5 out of 21. Okay, now another approach to that would be to look at it this way. If we're choosing 5 balls in total from the 10, how many ways are there to choose 5 balls, and how many of those ways include exactly 3 balls? Then what we could do is just take the number of ways that have 3, and it would be that out of the total ways of taking 5. And that would give us the same answer that we just worked out. So, one way to look at this is that we've got these 10 balls up here. 4 of them are blue, 6 of them are not blue, and we have 5 available spaces because we're taking 5 balls in total. Now, we're trying to work out the probability that exactly 3 of them are blue. So we could have the first one, the second one, and the third one, but we could also have the first one, the second one, the fourth one, or the first one, the third one, and the fourth one, and so on. Now, if we are trying to take 3 items from 4, then it's 4 choose 3, which is 4 factorial over 3 factorial 1 factorial, which is 4. Now, for every one of these, we're also going to have 2 other slots out of the 5 that we're choosing, where we may have one with that one, or it could be with that one, or it could be with that one, or maybe those 2 are together, or maybe those 2 are together. There are lots of different combinations. What we're trying to work out here is, well, we start with 6 and we're choosing 2. So that's 6 factorial over 4 factorial 2 factorial. Now, if you go to your calculator, you can work out what 4 choose 3 and 6 choose 2 are quite easily. Go to the keyboard, and if you go to the advanced bit here, you've got NPR and NCR. So if you put NCR in, we could do 4 choose 3. That tells us that that's 4. And we could do, the other one we were just looking at is 6 choose 2, which is 15. So if we just take that off to one side, there are then 15 there. So for every one of these 4, there are 15 ways. So effectively what we're doing is this times this, which is 4 times 15 ways that we can choose this in total. So 60. There are 60 total ways that we can have this. Now, 4 choose 3 times 6 choose 2 ways of getting the 3 blue balls, which we've just worked out. There are 10 choose 5 ways of getting the 5 balls from the 10 in the first place. So forgetting about how many are blue, there are, if we just fill up the 5 slots, we could have, for example, that would be one way, that would be another, that would be another, and then of course if we start to mix it all up, there are lots and lots of different ways. So there are 10 choose 5 ways of getting 5 balls from 10. That's by treating them all as distinguishable objects. So that means in total, from what we were looking at before, we have 4 choose 3 times 6 choose 2 ways that give us a successful 3 blues out of 10 choose 5 ways in total of getting those 5 balls, and that would give us, if we can do this on the calculator now, we're going to have 4 choose 3. So if I just bring up the keyboard, we're going to have 4 choose 3 times 6 choose 2, and that's going to be divided by 10 choose 5. So there we go, 5 out of 21, which is what we worked out before. We'll just add that now. It's, excuse me. Where are we? So we have 4 choose 3 times 6 choose 2 over 10 choose 5 is 5 out of 21. We can change that to a decimal if we wanted. I think it was about 23.81% would be the probability of that happening. So exactly the same answer as before. Now, in general, so what we have is the first part is the ways of choosing the number of successes you want from the number of possible successes. So we're looking for 3 blue balls out of 4 possible blue balls. Here is the way of choosing the required failures. So we needed 2 because there were 5 in total. So if we have 3 successes, there had to be 2 fails out of the possible number of fails, which was 6. So this is your ways of getting success times your ways of getting failure, and this is all out of the number of ways of choosing the however many objects you're choosing out of the total population. So it was 10 and we were choosing 5. Now this is the formula that's on your formula sheet. Here we have n, d, n and x, and the probability that x equals x, the probability that x equals 3 in the case we just had before, is your probability of successes here. So d, total possible successes, and the number of successes you want. Then n minus d, that ends up with the number of possible fails and the number of fails you want down here. And this is all out of the total number that are possible. So your total population and the total that you're choosing. So in our example before, it was 10 and 5. So for the 10 blue balls, 4 blue and 6 not, the probability we get 3 blue balls was 4 successes. So total successes was 4. X there is 3. That's what we want to get. We're left with 6 fails in the population, 2 possible fails out of the 5 that we're taking, and a total of 10 in the population, and a total of 5 that we're taking. Okay. Now, here's a different example using the formula. A parliamentary committee of 4 people chosen at random needs to be formed from 6 Liberal Party and 5 Labour Party members. Find the probability that 3 are from the Liberal Party. Okay. So, what I would always advise you do is write a short list like this out for your n, d, n and x and work out what they are straight away. So n to start off with is our total number of items in the population. So we have 7 and 5 making 12 people in total. And d is our total number of successes. Now we're looking for 3 from the Liberal Party. So in this case, success is a person from the Liberal Party. That would mean that there are 7 total possible successes. Now n is the size of the sample that we take. We are taking 4 people in total. So we're choosing 4, and out of that we're looking to see that what is the probability that 3 are from the Liberal Party, 3 are from our successes there. So in order to do that, we now just use the formula here to work it out. We have 7 choose 3. That's the total possible successes for us to get. There are 7 Liberal Party people and we're looking for 3 of them. For every one of those, there is going to be, well, there are 5 Labour Party people. It's going to be 5 choose 1, because that's how many are left, because there's only going to be 4 people in total. And that's out of 12 choose 4, because that's the total that we're picking. We're starting with 12 and we're choosing 4. So if we work that out, again, you can just do that on your calculator. You'll get, we could just use this one here if I overtype it. So 7 choose 3 times 5 choose 1, and that's divided by 12 choose 4. And there we got 35.35%, or 0.3535. Now, 3535. You can do this. So this is how you would do it, and that's an expression. You can build it without a calculator, and you wouldn't necessarily have to evaluate it without a calculator, but if you do have a calculator, you can work it out. The last thing I want to show you is how you would do that using the distribution. So go to interactive, distribution, discrete, because again it can only take particular values. Now we go to Hypergeometric Probability Distribution Function, PDF. This is going to tell us exactly 3. So we are going to solve here. We want x to be 3. N is the number that we're taking, which is 4. Now n is the total population size, and m instead of d. So, but it does tell us number of successes in the population. We know that that's 7. So even though the letter's different, we should be okay. Click it, and there we go. We get exactly the same value there. Okay. So last thing here. Hypergeometric is for problems without replacement, so you can't choose the same person or thing twice. Identify n, d, n and x, and this is the formula. Okay, that's it.